Today's video is about the Hadron Epoch. In this video, I'm going to give you a summary of the Hadron Epoch, then I'm going to take you a little deeper into the epoch. We're going to explore the process of particle creation as quarks get confined into various particles, and then we're going to look at the annihilation of these particles before closing out our discussion of the Hadron Epoch. First, an introduction. The Hadron Epoch follows immediately on the heels of the quark epoch. These are very early periods in the universe. The quark epoch ended at 10 to the minus 6, and at 10 to the minus 6, the Hadron Epoch begins. And it's going to last until 1 second. And during this period, quark-gluon plasma that we saw in the quark epoch is going to break itself apart into little bits. The epoch starts at 10 to the minus 6 with a temperature of 10 to the 13 Kelvin. At this point, the temperature is approaching a very special temperature. It's just on the edge of 3 trillion degrees. And at 10 to the minus 5, 3 trillion degrees was reached. So what happens at that moment is that the quarks now are in a low enough energy world such that they start grouping into 2s and 3s. Or in other words, they start grouping into mesons and hadrons. Mesons are quark-antiquark pairs that bind together and form a quark-antiquark particle. And to be clear, the antiquark is not the antiquark of the specific quark type. So for example, for this pion, which is a type of meson, you see an up quark paired with an anti-down quark. So because it's not an antiquark of the quark type particle, it's not an anti-up quark, that's why they don't annihilate, and instead they could coexist, but they only coexist for a very, very short amount of time, for 10 to the minus 8 of a second. Mesons are relatively irrelevant to our story because they decay so fast, but two other particle types that were made now are very relevant, and those are another type of hadron. A hadron is a particle made up of multiple quarks. It's called a baryon, and a baryon is made up of 3 quarks. Protons and neutrons, which we're more familiar with, are both baryons. To bring you up to speed with how quarks make protons and neutrons, there are 6 types of quarks, but 4 of them are unstable. The only 2 stable types of quarks are the up and down quarks, so protons and neutrons are made up of up and down quarks. A proton is made up of 2 up quarks and 1 down quark, and a neutron is made up of 1 up quark and 2 down quarks. And while a proton is very, very stable, it does decay, but its half-life is a lot longer than the history of our universe. Neutrons, on the other hand, do decay relatively rapidly, not 10 to the minus 8 of a second like a meson, but 10 minutes and 11 seconds is the half-life for a neutron. And that's going to matter a little later in the history of the universe than this video is covering. So, near the start of the Hadron Epoch, at 10 to the minus 5, the universe fills with particles, mesons, neutrons, and protons. To wrap our minds around the bigger picture, we have a universe that's expanding, and in it there is radiation, neutrinos, dark matter and dark energy, the Higgs field, gravity, and then the gluons of the strong force holding together a whole lot of protons and neutrons. And there's one more thing. There's a lot of antimatter. There are a lot of antiprotons and antineutrons. Just as this radiation was making up quarks and down quarks, this radiation was also making anti-up quarks and anti-down quarks. These antiquarks were swallowed up into their own particles, their own mesons and protons and neutrons. However, at 10 to the minus 4, the temperature reached such a point that the radiation could no longer spontaneously produce enough quarks to make these protons and neutrons and antiprotons and antineutrons. And at that moment, the protons and antiprotons and the neutrons and antineutrons, which had been colliding and turning into radiation and back again, up until now, they went through this final crashing into annihilation, where the protons crashed into the antiprotons and the neutrons with the antineutrons. It increased the universe's temperature momentarily by a lot, and it destroyed virtually all the protons and neutrons of the universe. Which brings us to a mystery. The fact that any protons and neutrons exist begs the question that we don't yet understand. Whenever we make particles in particle accelerators, there's no such thing as just making a matter particle. You could only make a matter particle and its antimatter particle twin. But if there are perfectly equal amounts of matter and antimatter particles being produced by the radiation in the early history of the universe, then all of them should have annihilated with each other, and we shouldn't have any protons and neutrons now. So why there seems to be this slight discrepancy between the amount of antimatter and the amount of matter in the early universe is a mystery. In the next video, we're going to turn our attention to the 1 second universe, the tail end of the Hadron Epoch and the advent of the lepton epoch.